So we've been looking at regression as a tool that gets used in forecasting, but also a tool that gets used in sort of analyzing complex situations statistically, so we can tell stories about what's happening and about causal relationships that sort of control for a variety of different factors. And regression gets used in all sorts of different situations. It's used in academic research. It's used in economic forecasts that are done by businesses and industries and banks and the federal government. And so it's a useful professional skill to be able to look at a regression analysis and sort of tear it apart and figure out what's happening. But it can also be a little intimidating, particularly because there's hundreds of different types of regression models and ways that these things can be configured. And so I'm going to try to do a crash course on how to interpret and make sense of some of the most common models. And I'll do that by discussing 4 or 5 different papers that have been published in PS and Political Science and Politics, sort of a general interest journal. These are kind of maybe lighter or more fun or more intuitive papers, but I'll kind of walk you through some of the models and what to look for. So this is a project that looked at the quality of Wikipedia coverage for covering state and local politics. And it's an analysis of the Wikipedia pages of state legislators. And so there's 3 different models here. There's one that's a probit model, which is similar to logistic regression, which we'll talk about later. The second is an OLS model, which is ordinary least squares. This is the kind of model that we have been looking at up until now, where we have sort of the equation of the line and we can sort of analyze those slopes and make sense of them. And then lastly, we have a Tobit model, which I'll sort of set aside, has some quirks about it, but I won't talk about that here. And you might say, well, why do we have these 3 different models that are all doing different things? It seems like they all have the same variables in them. If we look at the rows, sure enough, it's the same information in all those rows, that there's analysis that's done for all of those. And the reason is that different dependent variables require us to make different assumptions about how this regression process is working and what it is that we're actually producing, and therefore we need slightly different models. And so ordinary least squares regression, that model 2, that sort of middle column, is for a situation in which you have a continuous dependent variable. So interval ratio, it's sort of counting numbers that have mathematical meaning, and those numbers can take on basically any range. And so if we look down to the sort of note in that table, it's always nice when they give you a note explaining what you're looking at. It says in model 1, the dependent variable is a dummy variable, a dichotomous variable, 2 categories, indicating whether each legislator has a dedicated Wikipedia article. In models 2 and 3, the dependent variable is the logged character count of each article. So logged character count. So character count is how long the articles are, and logging it sort of creates sort of this diminishing return sort of effect. But it can still be 1 or 2 or 3 or 5 or 10 or 1,000. I think it can take on any of those values. And so we can sort of analyze that using an ordinary least squares model. But with the binary dependent variable, with the 2 categories, it's a little tricky, because I can get a forecast or a prediction out of that regression model that would say it's 0.25. Well, I only have the option of no Wikipedia article or a Wikipedia article. There's no scenario where you have 0.25 of a Wikipedia article. And so with probit, we're not thinking about it in terms of sort of changing the actual value in our forecast. We're thinking about it as shifting the probability. And so there's some math involved. I wouldn't encourage you to try to interpret those numbers in that column 1 in sort of an intuitive sense, other than sort of positive or negative, big or small. But what it's really doing is it's saying we're either increasing the probability or we're decreasing the probability of being coded a 1, of having a Wikipedia article. And so it's doing a similar kind of thing. We're telling this complicated story, but how we phrase what that forecast looks like, I'm going to get a precise character count, or I'm going to get a precise, presidential vote share, which we were looking at in our previous analysis, versus what's the probability of having a Wikipedia article, which is what we'll get out of that probit model. Okay, so hopefully that captures the basic big picture idea that different dependent variables require us to use different kinds of models because we're trying to make forecasts about different kinds things. When we're going in to analyze a model like this, I think that you should probably always follow sort of this 5-step checklist to kind of work yourself through it. And so step one, we've already done, right? Figure out what the heck your dependent variable is. Figure out how it's coded. Figure out, is the one having a Wikipedia article or not having a Wikipedia article? Figuring out what the range is. And that's going to be really important for how you make sense of that model. And also, it's going to be really important for knowing whether or not your model is likely to be an ordinary least squares model or some other sort of funky, strange, more sophisticated thing is required. So that's step one. Step two, look at your independent variables. And so these are the things that are sort of added in the rows. In this analysis of Wikipedia articles, they have whether somebody is a leader of the legislature, right? Years in politics logged, whether they're in the Senate, the upper chamber, the size of the district that they represent, the number of districts in a state, as well as their age, which maybe is associated with being sort of technologically savvy. Older people are typically less tech savvy than young people, and therefore are less likely to build their own Wikipedia pages, maybe. Level of education, whether you're high school or less, or whether you have a graduate degree, and then gender, female, male variable, whether you're a Republican, and then there's a constant. Constants are going to show up in a lot of models. Sometimes they're called intercepts. This is sort of your starting point, and everything sort of gets pushed up or down from there. So we're going to look at our independent variables, and then I'd say step back and say, if I'm trying to explain that dependent variable, if I'm trying to explain whether or not people have a Wikipedia page, or whether it's a long Wikipedia page or a short Wikipedia page, are these the kind of things I would want to look at? Like, are these the kind of things that would help me tell that story and make that prediction? And if you look at them all and they all seem reasonable, that's a good sign. If you don't look at them and say, well, I have no idea why you would, look at the number of districts in a state. I can't imagine why that would matter. Okay, maybe that shouldn't be in that analysis. But even more important, I would say, is when you sort of key in on things that really should be in that analysis. You're like, how is this not part of that story that you're trying to tell? This seems really important and left out. And so when we find those things that are maybe left out, that could be a red flag. It could be a sign that maybe this is an incomplete story and maybe we should take it with a grain of salt. On the other hand, you can't do everything. And on the other hand, not every thing that we think matters is something that we can get data on easily, right? I might assume that legislators will have longer Wikipedia articles if they're a blowhard or if they're a narcissist. But I don't have good data on whether or not a legislator is a narcissist, and so it's not going to show up in my analysis. And so we sort of have the big picture conversation. Does this seem like a reasonable way to go about thinking about this dependent variable? Third, we're going to look at the relationships between each independent variable and our dependent variable, right? So if you are a legislative leader, and I'll look at the probit column model 1, I'm going to go over and see that 0.51. It's a positive value, which means that it is pushing things up, right? And so it is increasing the probability that you're going to have a Wikipedia page. And intuitively, that makes a lot of sense, right? If you're in, a backbencher, maybe nobody bothered to make one for you. But if you're the legislative leader, if you're, brokering deals, odds are you have a Wikipedia page. That seems to make sense. Years in politics logged, right? So going over, again, I see a positive variable. I can sort of say, oh, well, the longer you've been in politics, that sort of pushes up the probability. If I jump down a little bit further, the age of a person seems to reduce their Wikipedia page likelihood. So it's pushing that down. Likely, if you're a Republican, that seems to push down the likelihood of having a Wikipedia page. So I can look at all those relationships and I can ask myself the question, does that seem reasonable? Is it pushing things in sort of the right direction? And sometimes it will seem very reasonable and I'll be able to tell a story. And at other times I might look at that and say, it doesn't seem like that quite plays out. But I should also keep in mind whether or not this relationship is statistically significant. And again, if you recall back to earlier conversations, statistical significance means if I assume a perspective of skepticism that there is no relationship out there, how likely is it that I will see the pattern I'm seeing in this analysis, right? So the legislative leader a pattern of 0.51. Like, how likely would that happen just by chance? And I convert that into what's called a p-value, or the probability of that happening. And if that probability is very low, let's say less than 0.05, 1 in 20 chance, and I say, you know, that position of skepticism that this is just random sampling variation, this result seems really unusual for that to be true. Maybe I should reject that sort of skepticism and say there probably is a relationship there. And if you look down to that note sort of at the bottom, it has sort of p less than 0.05, and has an asterisk associated with that. And it has p less than 0.01, which has 2 asterisks associated with it. And sure enough, it's very common practice with regression models for people to kind of flag what are these statistically significant relationships with asterisks, to sort of indicate to people, these are the patterns that are unusual enough that I'm willing to say, I don't think this is just random chance. And so if I'm going through here, being a legislative leader seems to be something more than just chance. But being in the upper chamber, even though it has a value of 0.321, even though it's positive, which I might expect, even though it's, you know, a fairly sizable number, I'm still looking at that and saying, I can't tell if that's just random sampling variation or something real. And so maybe I'm not going to put a lot of stock into it. So in addition to sort of understanding what those relationships look like, I also want to understand, are these relationships statistically significant? Are they unlikely to be just random sampling variation? Or more practically, are there asterisks next to the numbers indicating that I should pay more attention to these? All right, and then finally, I would say take a look at whether or not you think the model is doing a good job. And if we're working with ordinary least squares regression, there's a really simple way to be able to evaluate whether or not the model is doing a good job. There's the R-square statistic, which is the percent of the variation that we're able to explain in our dependent variable using our various independent variables in our model. And so if I'm in column 2 and I kind of go to kind of the bottom there, the R-square value is 0.241. I am able to explain 24.1% of the variation in character counts, logged variation, I guess, using this model. So I'm explaining some, but there's actually still a lot left that I'm not able to explain. And maybe there are things that I left out, like, is the person a narcissist and therefore is writing a lot about themselves on their Wikipedia page? Or maybe there's just random variation that has no bearing on anything, and I could never find variables that would really help to explain. It's hard to know, but we can at least get a sense of how good of a job this model is doing. For other models that are not ordinary least squared, it's less clear what the appropriate thing to pay attention to is to assess if the model is doing a good job. There's sometimes a pseudo R-square that gets reported. This ends up being really, really low. It's almost impossible to get a large pseudo R-square in my experience. Sometimes people look at sort of the predictive success. And so with that probit model, if you sort of assume that if you get a probability higher than 0.5, we'll count that as a 1. That's, you were likely. If you get a probability less than 0.5, you will count that as 0, not likely to have a Wikipedia page. And then we could kind of go through and calculate sort of the predictions for each case and sort of classify, did that match up? Was that correct? And kind of get a sense of, well, I was able to predict 71.6% of cases correctly. But it's hard to know exactly what the appropriate statistic is to look at or what the appropriate way to assess that is. But I think it's a worthwhile conversation to sort of ask yourself, does this seem to be doing a good job? Okay, so we've talked a little bit about 2 different models. I want to shift gears and kind of do this analysis a second time, this time looking at a ordinal regression. And so this is a analysis of people's likelihood of voting and how their perceptions of media bias and their belief that there's voter fraud is affecting their willingness to go and actually vote. So the dependent variable, always the place you start, is a 5-category scale with 1 definitely will not vote and 5 definitely will vote. So positive values in our table are going to push things up toward making people more likely to vote. Negative values are going to push things down toward that 1 category of definitely will not vote. So we've figured out what our dependent variable is. Because these are ordinal categories, they're not sort of like something that you can count mathematically and do addition, subtraction, and division on, we're treating these as sort of, they have an order, and we're using a regression model, ordinal logistic regression, that is able to sort of take into account that those are sort of discrete categories. Nothing falls in between, and you only have 5 of them. We've got our independent variables. We've got the age in years. We've got education. I think that's a 4-category scale. We've got sex, female is 1. We've got race, where we're indicating if a person is Black with a 1, not Black is 0. Ethnicity, Hispanic 1, not Hispanic 0. There's a index for the interest people have in the campaign. There's a variable for party ID, which I forgot to look up what that means. And there's a question about how likely do you think there is voter fraud, and how likely or how biased do you think the media is. And so I'll just sort of go through and analyze the second model that includes the voter fraud variable. And I can say, okay, so I'm looking for the relationships. Older people more likely to vote, that makes sense. Education more likely to vote, that makes sense. Women are more likely to vote. African Americans are more likely to vote. Hispanics seem less likely to vote. Negative value, negative 0.83. More interest, more likely to vote, positive values there. Party ID, again, I forgot to figure out which direction that was. And then voter fraud. The more voter fraud that you think there is, the less likely you are to vote. Negative relationship. So it's pushing down our prediction. It's moving us toward that 1 category away from the 5 category, right? And that makes sort of intuitive sense. I think I can like buy that story. I can also flag what things are statistically significant. It's age. Strangely here, the asterisk got put on the parentheses numbers. Those are the standard errors. We'll talk about those in a little bit. There's maybe a reason why you would do that, but I find it less intuitive. So age in years is statistically significant. Education is, being Hispanic is, but sex and race are not. Campaign interest is statistically significant, and then voter fraud variable is statistically significant. That seems to be driving things more than just random sampling variation would expect. And so we can look at that, and we can say, I think this captures most things that I'd be interested in, and I can interpret those relationships and whether they're statistically significant, and be reasonably confident with this analysis. This is sort of similar to that probit model we were looking at earlier. Probit seems to be a little bit less common than what's called logistic regression. This is looking at that same paper about voter fraud and media bias, but this time asking the question not how likely are you to vote, but will you vote for President Trump, yes or no? And so again, we can look at that second column where it includes the voter fraud and media bias variable. And I can know that I'm looking at a 2-category sort of thing. And so I'm thinking about the probability of voting for Donald Trump. And I can look at all of those relationships, age, education. More education seems like less likely to vote. Sex, female 1. If you are a woman, you are less likely to vote for Donald Trump. That again seems to square with my understanding of sort of how the 2016 election played out, which this is in reference to. Again, race, if it's coded 1 for Black, if you're Black, you're less likely to vote for Donald Trump. I think that makes sense. We can sort of go through this and say it more or less makes sense. And when we look at the voter fraud and the media bias, the more you believe that there's bias in the media, and the more you believe in voter fraud, the less likely you are to vote for Donald Trump, which sort of suggests that that rhetoric maybe discourage people from actually showing up to polls and voting for Donald Trump, which is sort of what we were saying earlier, which is, I think, maybe an interesting story to tell. And when we get pretty good at interpreting these regression models, you get to a point where you can kind of just scan through the coefficients and the variables and start telling that story almost like an automatic thing. Like, in our analysis, it looks like the more education individuals have, the less likely they are to vote for Donald Trump. That becomes something that just automatically pops once you've identified what the dependent variable is, and you've keyed in on that negative 0.52 in the education column 2 sort of area, and sort of interpreting that as a reduced in the probability. Okay, I'm going to give you a third or fourth type of model. This is a Poisson regression. So maybe French sounding, I'm not sure. The study is looking at the proliferation of New York Times national news desk stories. And we have to drill down a little bit more to figure out what that dependent variable is. But in this case, the dependent variable is a count variable. And it's the number of newspapers that picked up a New York Times story that had been sort of put out on their wire service. And because counts sort of stop at 0 and count up from there, there's some sort of statistical quirks that sometimes people use different types of regression models than just OLS to analyze. And a Poisson model or a negative binomial model are designed for count variables specifically, but the analysis is still pretty much the same. I know that my dependent variable is a count variable, so the higher the value, the more likely stories are to be picked up, the more viral they've gone. I see an intercept, right? That's my starting point. I'm not necessarily going to interpret that in any sort of meaningful way, but I have a couple different variables. And so the New York Times article word count has a positive value, longer stories get picked up. Prominence in the New York Times, I think front page has a higher value, positive effect. And then what this paper was really looking at is what happens when a story includes a dog in it. Dogs are apparently popular. People like dogs. And it turns out that if a story contains a dog, it has this increase in the likelihood of their count of 0.968, increases that count. More newspapers are likely to pick it up. In fact, that effect is not all that different than having a front page story on the New York Times, which is, I think, kind of interesting that people do like dogs. And that shows up in our news coverage. But the next thing that you're probably looking for is, okay, where's my asterisk? Like, where's my measure of statistical significance? And I'm really annoyed at this one because there isn't one. It's not that some of those findings aren't statistically significant. It's that the authors didn't bother to put in the asterisk to flag that for us. And they didn't give us p-values either, which would be the other way to kind of pick this out. If you just tell me that the p-value is 0.0001, I can say, well, that's really small. That's really unlikely to happen by chance. So how do I do this? Well, the rule of thumb is this. If your standard errors, and those are the numbers that are reported in parentheses, are half of what your coefficient is, if what your slope is, then it's statistically significant. And the reason for that is going back to our formula for hypothesis testing, which is your null hypothesis minus your finding. So essentially whatever your finding is. So if we're looking at the dog story indicator, we've got a 0.968. Let's say that that's the distance away from the null hypothesis that we have. And I want to understand that distance on the sampling distribution, which is what would happen if I took other samples of 352 articles and plotted the results. And I would sort of get this imaginary sort of like all of the various possible samples. And I'm trying to put my sample on that distribution. It falls somewhere, I'm not sure where. The way that I put it on the sampling distribution is to think about how many standard errors it's away from 0. And so I'm essentially dividing that distance by our standard error. And if I'm out one standard deviation, standard error on the sampling distribution from my hypothesis, that can happen. If you remember, the sampling distribution is a bell-shaped distribution. If you go out one standard deviation or standard error on the sampling distribution, that captures about 67% of all the samples that would fall in that range. But if you go out 2 standard deviations on the sampling distribution, that covers 95% of all the samples sort of fall within the middle. And so if you're out there at 2, that's a pretty good sign that you're out there in that like 0.05 range. That's kind of an unusual kind of finding to fall that far away from the null hypothesis of 0. And if you're out, well, in this case, let's see, it's 9.68 divided by 2.31. I'm going to kind of round and say close to 4. Well, that means I'm out 1, 2, 3, 4. I'm like way out in the tails. The probability of that happening is really small. If you go out 3 standard deviations, that's 99.7. So I'm way less likely than that, or than that 0.03. So I can say I'm out so far from that null hypothesis that this has got to be a statistically significant relationship. If That's not an intuitive way to think about this. The rule of thumb is if your coefficient, if your slope is twice what your standard error is, that's probably a statistically significant relationship. And so I can sort of eyeball that and say, well, the dog catcher story indicator is statistically significant, and the prominence in the New York Times is statistically significant, but the word count is not. Okay, I want to flag one last model because this one's a little bit weird, but it does something that I think is important. This is a study of presidential scandals and the duration between when a scandal strikes and when it ends. And it ends when somebody resigns. And so let's say that President Joe Biden nominates somebody for Health and Human Services, and that person has a scandal of some kind. If it's a personal scandal or a financial scandal or whatever, once that's reported, how many days go by until that person resigns their position? That's what we're looking at here. The problem with that kind of a measure is that it's tricky. We can certainly count the days between when a scandal starts and when a person resigns, but what do we do if we count and count and count and they reach the end of the term and they never resigned? Well, they're out of office, but if that term had been longer, they might have continued to stay in for longer and longer and longer. So we say that it's censored. We don't get to view all of the potential time that could be there. Likewise, what do I do if I've hit today? If there's an ongoing scandal and I don't know if this person is going to resign tomorrow or in 20 days, or if they're going to hang on to the end of the term, again, I can't observe the full length of that duration, and it's censored. And so we have special statistical models that are designed to sort of handle those kind of situations. And normally I would say, well, you analyze it just the same way, right? You think about your dependent variable, you think about your independent variables, and you interpret your coefficients. And that's true, except that this one's a little bit different. The numbers that are being reported are not slopes the way that we were looking at with ordinary least squared, and they're not really coefficients or slopes the way we were looking at with the other models. They're hazard ratios. And so it's sort of been mathematically adjusted a little bit, in theory to be more intuitive, but I've never found it to be more intuitive. So a hazard ratio, I'm quoting directly from the article here, because again, I always get these mixed up in my head. So sometimes you do have to go back to the article and actually read to figure out what the heck it's doing. A hazard ratio less than 1 indicates an increase in the duration to failure. How long does it take before the person resigns? That is getting longer. And so I'll look at the presidential approval in model 1, that's sort of in the middle there, the 0.992. So that's less than 1. And that actually kind of makes intuitive sense, right? If it's less than 1, that means that the president is as the president is popular, the person is going to be able to hang on longer. Whereas if the president was unpopular, they might get thrown, overboard quickly as a way to minimize the damage. And then hazard ratios greater than 1 indicate a decrease in duration. So if I have things like GDP change, right? So if the economy is growing, maybe I don't want that scandal to take away from that story, and so I might push out a member of my cabinet more quickly, because they're distracting from the good news that I want to tell. Maybe that's the story. Because that coefficient, because that value, that hazard ratio is positive, it's accelerating us toward that point of failure. It's shortening that point of failure. Again, I don't know that that's the most intuitive way to think about this, but once we've sort of made the shift and once we've sort of recognized, okay, these are hazard rates, I interpret them a little bit differently. Instantly, they're all positive. There are no negative numbers here. Then I can make that shift, and then my interpretation of the asterisk as statistically significant makes sense, and I can tell the story about what's happening in this model. And I'll flag that hazard ratios show up not just in duration models, although they are probably the most common there in duration models, but in some logistic regression and some binary or probit regression, where you're looking at that 0-1 probability. Sometimes people will report odds ratios rather than the coefficients. And again, you just have to read the fine print, know what you're looking at, so that you can interpret it correctly. And the more you do this, the easier it gets to be able to sort of look at the tables and pull out the story very, very quickly.